In today's video, we're going to be talking about position time graphs. After watching this video, you should be able to interpret some position time graphs and kind of understand what's going on and be able to determine the slope of a position time graph. So let's get right to it. Motion graphs basically describe motion of an object, and doing that in words can a lot of times be challenging. I personally always say a picture is worth 1,000 words, and so that's kind of what a graph is. It's like a picture of something that's happening, and so a motion graph is going to describe the object or the motion of an object. Couple things to remember, just because I'm going to use some words and just want to make sure you guys don't forget about what these mean. Motion is a change in position measured by distance and time. Okay, so if something is moving, we measure it relative to something. How much has it moved away from something and how long did it take? Speed tells us how fast an object moves, and velocity is, remember, a vector quantity, which means it has a magnitude, so a numerical value, and a direction associated with it. And then acceleration tells us how quickly speed and or direction changes. Okay, I always like to think of acceleration as how much does velocity change. Okay, acceleration is how much does velocity change. Okay, so let's start talking about distance time graphs. Plotting distance against time, or d versus t, can tell you a lot about the motion. And so if we look at our axes, time is always plotted on the x-axis. Time will always go on the x-axis, or the bottom of the graph. To the as you move to the right on the time axis, time is increasing. So this is going to be like 0, and then as you move to the right, it's getting bigger. Okay, so it's getting bigger. On the y-axis, or on the left-hand side, distance is plotted. And the higher up on the graph you go, the further from the starting point typically. Sometimes you're going to see graphs where the 0 is actually here. It's in the middle. Okay, so don't let that throw you off. And when we get to that in the notes, I'll point it out. All right? So if an object is at rest or not moving, how is that plotted on a distance versus time graph? Well, it's actually very simple. It's a flat line, because think about it. Time never stops, right? It just keeps on going. So as soon as you start your stopwatch, and let's say you're going to time how fast the rock moves. So you start your stopwatch, you look at the rock. Has that rock moved at all? It hasn't. And so its distance stays constant, whatever you want to say. Maybe this is where 0 is. Stays constant, but time continues to pass. So if you see a horizontal line on a distance versus time graph, it basically means it's not moving, okay? So it keeps the same distance throughout the time, but time continues to increase, but the distance doesn't change, so it's at rest. Because this is an example of at rest. Something that's undergoing constant speed basically means that the object is moving at the same speed throughout. So I'll just make up some number. Let's say 3 meters per second. So it's going to constantly move at 3 meters per second. No matter how much the time changes, it's always moving at 3 meters per second. So time will increase to the right, but as time passes, what happens to the distance from the starting point? It too increases. And what you end up getting is a straight line. Okay, so constant speed is thrown by a straight line. Okay, so this is an example of constant speed, this line here. Okay. You'll notice there's 2 lines here, actually 3 lines. Whoops, sorry. Each of these lines, what's different about them? Well, they all show constant speed. Okay, they all are straight, right? But one is faster than the other. Okay, this one is really fast because notice it covered a whole bunch of distance in a very short amount of time. This one I guess we could call like medium because it covered a average amount of distance in a certain amount of time. And this one is relatively slow. It didn't cover much distance in the same amount of time as, say, the blue one. Okay, so being able to interpret the graph is really important, and this takes a little bit of time to get used to. And once you get it, it's like this is not such a big deal. Now, remember, things can have negative velocities. Okay, and negative velocities basically indicate a direction. Okay, it's not that it's like going backwards in time, if you will. Remember in one of the previous lessons, I talk about sign conventions, and typically in our class, we're going to use to the left as negative or down is negative. And so if it has a negative velocity, that's just indicating that it's either moving left or down, okay? So this object, whatever it is moving at a constant velocity. There's no change. You can make some number up. We'll say 3 meters per second again, but it's moving 3 meters per second to the left instead of like to the right, okay? And this, again, is kind of a same thing I was talking about 2 slides ago. It says, let's look at 2 moving objects. Both of the lines in the graph show that each object moved the same distance. Okay, notice the same distance was covered. Okay, but the steeper dashed line, the red line, got there before the other one in a shorter amount of time. So which line is moving faster? If I were to ask you, is the red line or the blue line moving faster? Well, this red line indicates fast, and this blue line indicates slow. Okay, and it's just because, notice, the blue line took this much time to get to the same point that the red line did, okay? So again, being able to interpret graphs is pretty important, okay? So a steeper line, this is always true, a steeper line indicates a larger distance moved in a given amount of time. So in other words, a higher speed. Both lines are straight, so what does that mean if they're straight? They both have a constant speed, so they're both traveling at constant speeds. Maybe the blue one's at 1 meter per second and the red one's at 3 meters per second. Okay. So the slope of the line actually tells you something, okay? And the slope of the line in a position time graph reveals the velocity of the object, And this is just a kind of a cute saying, as the slope goes, so goes the velocity. So if you have a steeper slope, you have a bigger velocity. If you have a not so steep slope, you don't have a very big velocity. Okay, so they're directly related. And I just noticed I spelled slope slop. That's kind of funny. All right, anyway, if the velocity is constant, then the slope is a straight line. And now this is the new piece we're adding in, and I'll show you examples of this as we go. If the velocity is changing, so let's say there's a change in the velocity, like it starts off at 3 meters per second and then it drops down to 1 meter per second, then the slope is now a curved line. Okay, it actually starts to be a curved line. It's no longer straight because it's not a constant velocity anymore. So let's take a look at that. So first, I'm going to do a straight line. Okay, and again, I am not the best artist, so I apologize. So time goes on the bottom, distance is on the side, and if I draw a straight line, as straight as I can draw it, this means that it has a constant velocity. Okay, and we can make something up. We'll say 3 meters per second. We could figure it out if I had numbers on my axes, but I don't, so we just make something up. All right, I'm going to make a bigger one here for my curved line just to kind of show this a little bit better. Let's say it looks something like this. Okay, this is a curved line, and so it is a curved slope, I should say, so it is not a constant velocity. And I'm going to change pen colors here. You'll notice there's kind of like, we'll break it into 2 parts. This piece here, notice the slope isn't very steep, okay? And so the object must be traveling slower here. Because remember, as the slope goes, so does the velocity. And so it must be traveling slower here. Whereas on the right side of my yellow line, you notice the slope is much steeper. It's much more inclined, if you will. And so the object must be moving faster here, okay? And so this is just indicating that this is a changing velocity. That's the point. Okay, if you have a curved line, the velocity must be changing as time passes. Okay, which we're going to talk about later on means there's some acceleration occurring. Okay. All right. So the slope of a line on a position time graph is equal to the velocity of the object. Right. If the object is moving with a velocity of 4 meters per second, then the slope of the line will be plus 4 meters per second. If the object has a velocity of 0 meters per second, then there'll be no slope. It'll be a flat line. Okay, and so really, once you get it, it's like, oh, this kind of makes sense. At least I think. Maybe you guys will end up disagreeing, but at least I think it does. So there is an equation for slope, and this basically is right from math class, right? Rise over run. Okay, so you can write all this if you want. If you have a different way of remembering it, be my guest. But basically, it's change in the y-axis over the change in the x-axis, or in the end, rise over run. Okay, so y2 minus y1. These here are just steps to calculate slope. Okay, they are just steps to calculate slope. okay, right there. So you can read through those, write them down if you want, but if you feel like, oh, I get this, then don't worry about it. Okay, but you'll only need to be able to calculate the slope of some graphs. So let's do a practice problem, shall we? So here is a position versus time graph. First question I might ask you is like, is this velocity constant or is it going to be changing? And hopefully, using your noodle, you'll realize that this is a constant velocity. How do I know that? Just by doing nothing right now. Basically, I know that because it's a straight line, right? Constant velocity is associated with a straight line. Now, what is the velocity of this object? Well, that's where we're going to use delta y over delta x, or we're going to calculate the slope, in other words. Or some of you probably are more familiar with rise over run. Okay, so what is my change in the y positions? Okay, I start at 5 and I end at 25. Okay, so I put my last coordinate first, 25, which is right here, and my first coordinate last, if that makes sense, minus 5. So you subtract them, 25 minus 5. So that's my rise over my run. So I start at 0 and I end at 5. And I remember I put my last coordinate first and my first coordinate last, if that makes sense. So my final time is 5 seconds minus my initial time, which is 0 seconds. So 5 minus 0. Okay? And if you do that in your calculator, or even your head, it's 20 over 5, which would equal 4. And what is this? Meters per second. Okay? Notice here's meters, here's seconds. Man, everything is working out good. Life is good. That takes care of today's video. I'll see you guys next time.